And now on to confirmatory factor analysis. So in order to talk about this, we're going to first introduce the idea of scale development, because confirmatory factor analysis is very often used within the context of scale development. Okay, so some terminology to start out. When we talk about scale development, we're talking about surveys like this one on the right here, where you have a set of questions and you're getting people to answer those questions based on a predetermined response scale. So the construct is going to be the thing that we want to measure. In this case, we're measuring ethnic identity. The scale is the set of items in order to measure that construct. The scale is also called a measure. So sometimes you'll hear both the scale and a measure to refer to the set of items. And the items are the particular statements that the participants are responding to. So this is a statement right here. I don't try to become friends with people from other races, ethnicities. The response scale, not to be confused with the scale itself, the response scale is how you respond to a particular item. So in this case, this response scale has 5 options: strongly disagree, somewhat disagree, neither agree nor disagree, somewhat agree, and strongly agree. And generally, we're going to convert these options into numbers. So this would be 1, 2, 3, 4, and 5. So those are some just preliminary things to talk about when we are thinking about scales, and it's going to matter for our confirmatory factor analysis. So some of the major questions that we have when we're developing scales is, what is the construct? You have to theoretically determine what the construct is. Does it have subdimensions? Are there certain parts of the constructs that feed into the overall whole? And do the correlation between the items in the survey we asked correspond to the way that we think about the construct? And this is really where we're going to be focusing in on the CFA analysis. Does the scale actually measure the construct? So that's a question of validity. And do different kinds of people respond to the items in the same way? We're going to get back to this with CFA when we go into measurement and variance. But right now, we're really going to focus on question 2 to some certain extent, and mostly question 3. All right, so the scale, the construct we're dealing with today is ethnic identity development. So back in the 90s, Finney proposed that there's 2 dimensions of ethnic identity development, and she was basing this on general identity development by Garcia. So there are these 2 components: exploration, which is how much you've explored your ethnic group membership, and commitment, how much you feel a sense of resolution about who you are and what your ethnic group means to you. Okay, so to measure these 2 constructs, Finney created a multi-ethnic identity measure, which we usually refer to as the meme. And well, I guess it says recently, but that was many years ago. So in 2007, Finney and Ong revised the meme and created the meme R. So the meme originally had 14 items, the meme R has 6 items. And so we're going to be dealing with the meme R, those 6 items today. So some research questions that we could have about the meme R would be, is ethnic identity as measured by the meme R 1 dimension or 2? And do these items measure the subdimensions of the meme in the way that we think they do? All right, so now let's get to the structural equation modeling part of this research. So as we saw at the beginning of class, you're going to have observed variables and latent variables. These 2 variables connect in a very special way in confirmatory factor analysis. But just to review, observed variables are going to be directly measured, and they can be continuous or categorical. In CFA, they're always going to be continuous. So let's just skip right there. For latent variables, these are going to be the constructs. They're not directly observed, but they're determined by the indicators. That is, the observed manifest variables. These are continuous for now, and some of the other things we call them are unmeasured variables, factors, constructs, and true scores. So you'll notice here that we call our latent variables constructs because we think that they're measuring the construct that we are associating them with. But you'll also hear factors quite a bit. All right, so latent variables are going to have 3 main components. The factor, the latent variable itself, is the construct that we think explains the relationship between the indicators. Those are the observed variables. So one thing to keep in mind is that we can call the factor whatever we want, but it doesn't mean it's actually representing that. right? So there's this disconnect sometime between the factor as indicated by the items and the actual construct that we were trying to measure. So you gotta sometimes make sure you don't have too much drift between those two things. So an example is I might call my factor engagement in school, but if all of the items are about how many video games you play at school, then that's not exactly like general engagement. That might be engagement in, your video game learning, right? So you can see how the items that you choose can really determine whether or not your construct is really being measured accurately. Another example could be if you're measuring interest in baseball, right? You could have a lot of different things that kind of tap into your interest in baseball. How many games do you go to? Do you watch the games on TV? Do you buy baseball cards? But if you're mainly basing your construct on things that require like a lot of money, so like buying baseball cards, going to games, you might be missing out on some of the other types of indicators, like the fact that you have memorized all these statistics about your favorite team, or that you wear your team's t-shirt every single weekend, those kind of things. So that's about making sure that the statistics line up with the actual theory. All right, so that's the first component, is a factor. The second component are the indicators. So these are the observed variables that you are going to be using to measure the factor. The direct effect between the factor and the indicator is called the loading. Once we get to the interpretation, you'll see that this is just a regression coefficient. It's just a slope. But in CFA, we give it a special name called a loading. Note that the arrow goes from the factor to the indicator because we are assuming that the general construct of interest in baseball is what's causing you to perform on this indicator, so buying baseball cards. So let's see. Our factors, our indicators can also have what we call error terms. And if you remember back from path analysis, all of our endogenous variables have an error term associated with. And since our indicators are endogenous variables, they do have error terms associated with them. And these error terms will have a variance, as we've seen. A special thing that we do when we're looking at CFA is that we can allow these error terms to correlate. So we're drawing relationships between our error terms. And I'll talk a little bit about why you might do that later on. All right, so here are the 6 items that are in the meme R over here. And then these are research questions. Is ethnic identity as measured by the meme 1 dimension or 2? So in order to answer this question, we're going to do 2 models. One model is going to have 1 factor with 6 indicators. So basically, we're going to have 1 factor with all 6 items predicting it or being predicted by it. And we're also going to compare a model that has 2 factors and 3 indicators each. So basically, our second model will say that these 3 items measure exploration, while these 3 items measure commitment, okay? And then our second research question is, do these items measure the subdimensions of the meme, which is exploration and commitment, in the way that we think they do? Does the model have overall fit, adequate fit overall? Does each item have adequate loading on its factor, and are any of the correlations justifiable? So we'll get into detail about what that looks like. All right, so here are some diagrams. For our first research question, we're going to compare a 1-factor model where ethnic identity, the construct predicts 6 different indicators, is composed of 6 different indicators, all 6 items. And the second model is where we have 2 factors, exploration and commitment, and each of those has 3 indicators. Here are the equations for those 2 different models. So for our 1-factor model, we have one factor. And so the factor, so if you notice that since the arrow is pointing at our indicators, we're going to have 6 equations, one for each indicator. And the one predictor in that is going to be the factor. So ethnic identity predicts mean 1, mean 2, mean 3, mean 4, 5, 6, so on. Because these are endogenous variables, each one has an intercept and each one has an error term. So you see that error term down there. Now in our 2-factor model, we still have 6 equations because we have 6 indicators. But in this case, mean 1, 2, and 3 are being predicted by the factor exploration, and mean 4, 5, and 6 are predicted by the factor commitment. So that's the only difference between these 2 models. And but we still have the same intercept and error term for each of those 6 equations. All right, and now let me show you the syntax for these 2 models. So this is Stata up here, as we've seen before. Well, this is actually a little bit different. So what we've seen before is we would have our dependent variable with an arrow facing toward it, and then our independent variables. Instead of writing these 6 equations as mean 1 being predicted by ethnic identity, mean 2 being predicted by ethnic identity, we can do a shorthand and say ethnic identity is the factor predicting mean 1, 2, 3, 4, 5, and 6. Okay, so the really important part here is that this arrow is facing our indicators, because we are saying that this latent variable is composed of those indicators, and it's facing, the arrow is facing because these are the dependent variables, but it might help you to think of this latent variable is composed of these indicators. Another special thing in Stata that happens is that with Stata, latent variables need to start with a capital letter, and observed variables need to start with a lowercase letter. So if you're getting some errors, especially if it says something about not identified or something about latent variables, then you need to make sure that you have lowercase letters for your indicators and uppercase letters for your latent variables, your factors. Okay, and so then for the 2-factor model in Stata, here you see exploration is composed of mean 1, 2, and 3, and commitment is composed of mean 4, 5, and 6. Now in R, we have some new syntax as well, or completely new syntax. We're still using this model command, but here we have the name of our factor, and we're going to use this notation to say this is a latent variable that is composed of these 6 items. So use equal signs, tilde, to say mean 1, 2, 3, 4, 5, and 6 are going to be the indicators of that latent variable. When you're doing exploration and commitment, you're just going to see exploration on one line and then commitment on a second line. All right, and so then going back to our diagram here, you will see that there is a correlation between exploration and commitment here, and that is going to be a default in all of our programs. Because exploration and commitment are exogenous variables, the programs are going to assume that they are correlated. All right, so research question number 1 is, which model fits better? So these are fit indicators for a 1-factor model. You can see the chi-square is pretty high, but we also have a relatively large sample size. RMSEA is way above what we would like it to be. CFI is just below what we would want. We want 0.9, and SRMR is kind of above, it's below 0.10, which is okay, but it's not terribly low compared to our 2-factor model, where you can see that chi-square is a lot lower, it's 10 times lower. Our RMSEA is right at 0.05. Our CFI is pretty perfect, and the SRMR is very low. So in comparing these 2 models, we can just look at it pretty clearly and say, okay, the 2-factor model fits better than the 1-factor model. So this two-factor model is reproducing the correlations between the 6 indicators much better than the one-factor model does. So that's pretty cool, right? So we answered one research question about the meme. Is it better to think of ethnic identity as just one thing with these 6 items, or is it better to think of ethnic identity as exploration with 3 items and commitment with 3 items? This data is suggesting that thinking of ethnic identity as exploration and commitment is a much better fit to the data. All right, on to our second research question. Do these items measure the subdimensions of the meme in the way that we think they do? And to answer this, we're going to look at, does the model have adequate fit? Does each item have an adequate loading on its factor? And are any correlations justifiable? So here's those fit indices again. As we already saw, these are all adequate or good fit. So this is our two-factor model. We can see that it looks really good. So that answers that question, right? We have a good sense that that this is how the data is representing these 6 items. Next, we're going to look at the factor loadings. Now remember, the factor loadings are the regression coefficients. Okay, so first thing to look at this table, that these are the standardized coefficients. When we're doing CFA, we are almost always going to look at the standardized output. Okay, and there's a special reason for this that we'll get to when we talk about scaling latent variables. But right now, we're always going to look at the standardized output. And you notice here, because each of our indicators is our dependent variable, we're going to have one, set of rows for each one. So each indicator is going to have a intercept right here. So that's the constant. So this, if you're going back to regression, you know how to interpret that as the average when all the predictors equal 0. Whenever we have a confirmatory factor analysis like this, we're always going to have one predictor, and that's going to be our latent variable. So here, our predictor is expiration. So we're saying that for a 1 unit increase in one standard deviation unit increase in expiration, the mean one increases by 0.7966 standard deviation units. That would be the typical regression-based interpretation of that. Generally, though, when we're looking at factor loadings, we're going to do a more holistic view of it. We're not going to interpret each intercept and coefficient like that. What we're actually looking for is for these standardized loadings to be above 0.7. 0.4 is kind of like a baseline, but you really want to be like 0.7, 0.8, like that's really a good number. Because why, right? These standardized loadings are essentially correlations between our factor, between our unobserved construct and the item indicator. And if you remember back from regression, the square of that is going to represent the amount of variance that's in the indicator that's explained by the independent variable, which in this case is the factor. So you want your construct to be explaining most of the variation in each individual item, because that means then that that item is actually measuring that construct. So, if we have 0.4, then that means we're at 16% of the variation in this one item is caused by this construct. But really, wouldn't you want at least half of it? Yeah, so that's where you get to the 0.7. 0.7 is where you have 49% of the variation in an individual item being explained by your latent construct. So that's where that number comes from. That's why we want to see a 0.7 in these standardized loadings. And we'll talk about where some of the other variation could be coming from a little bit later. But so you want high loadings as close to 1 as possible, above 0.4 at least, above 0.7 ideally. So what if you have some low loadings? Sometimes you want to remove the indicator if it's going to give you enough to actually do the analysis. In this particular analysis, since we only have 3 items per indicator, we're going to have some trouble if we remove one of them. So we really want to keep them. But what you might want to do is allow the error term to correlate somewhere. And we're going to get to that in a little bit later. So just put a pin in that. And the other is that you can move the indicator to a new factor. And when you look at the modification indices, that's where you're going to see that that might be a possibility. Important thing to consider is that you do not want to do what's called reifying the construct. Like I said, there can be some disconnect between what you think you're measuring and what you're actually measuring based on the items. So what you don't want to do is start moving items around because you think that it measures a certain thing when the data is telling you this isn't quite how this works. If you get to this point where you're just kind of moving things around because it feels right, that's where you need to take a step back, go back to the theory and try and figure out what is it that I need to do. Tinkering with the model just a little bit at a time is not going to be the path always. All right, so going back to our research questions here, we're now looking at, does each item have adequate loading? Yes, we're 1.7 on most of those, and are any correlations justifiable? The only correlation we have here is between exploration and commitment. And because this is our standardized output, this is a correlation 0.73, which is pretty high. So in general, if you have two separate constructs, you want to have that correlation be low to moderate to really say that they are distinguished things. But in this case, the solution here would be to combine them into one factor to say, okay, well, if exploration and commitment are almost the same thing, then they could just be one factor under ethnic identity, right? But you remember, we already tried that. We did that analysis already, where we showed that the model with just one factor did not fit as well as the model with two factors. So it does seem better to say that exploration and commitment are the two factors of ethnic identity. And they are very highly correlated. So if you've explored your identity a lot, you are definitely more likely to have said that, yeah, I feel this is a commitment to my identity. So that's reflected in the data. It's theoretically supported. So we're gonna be okay with that. And this is actually something where you can look at other people's research too. And this high correlation is very common in ethnic identity research. All right. Then if we did have some poor fit and we wanted to tinker with this model a little bit, we could take a look at the modification indices. And so again, we're going to be looking at what are our highest modification indices and what are they telling us to do. Here we have two modification indices that are the same highness. So the first one would be having mean 5 being predicted by exploration. Right now, mean 5 is a commitment item, and so this would be saying let's cross-load. That's the term, cross-load mean 5 onto explorations. Let me show you what that would look like. That would say here, boom, add this arrow and have exploration predicting mean 5. So first off, one, you don't want to do this because is mean 5 like part of exploration? Let's go back to that item. I understand pretty well what my ethnic group membership means to me. Maybe that's an outcome of exploration in the way that commitment is an outcome of exploration, but it's not necessarily the same thing as exploration. So this is a case where you have a correlation that's telling you to do this. The modification index is saying, hey, do you want to do this? And you would say, no, I don't want to do that because that's not theoretically supported. The other thing down here is allowing a covariance between the error terms of mean 4 and mean 6. Now, this is something that we can actually consider. This is suggesting that there is some variance that is shared between these two items. So what are these two items? One is I have a strong sense of belonging to my own ethnic group. The other is I feel a strong attachment towards my own ethnic group. So there's some similarities, but is that similarity more than what you would just get from the fact that they're both exploration, both commitment items? All right, let's break this idea down a little bit. So the fourth component of lane variables is the variance. For all of the indicators, we're trying to figure out how much of the variance comes from the factor and how much is coming from everything else. So in confirmatory factor analysis, we're dividing the variance into common, specific, and error. So the first source of variance is going to be common variance. So that's right here. That should be the most, that should be the highest percentage, at least 16%, and ideally more than 49%. So this is the amount of variance in the indicator that's coming from the factor. So that's what the loading indicates, the amount of variance that's coming from the factor. You might see in some exploratory work, factor analysis work, this idea of communality, which is the percentage of total variance that's shared among the indicators. But this idea of common variance is based on the fact that if all of these items are related to each other, it's because they're measuring some broader construct, right? So that's where we get this idea from. But the factor is never going to explain all of the variance. And so in that case, we have something called unique variance that we can divide into two things. So the unique variance is divided into error variance. So that's just random noise that you can't control. And then specific variance is something systematic that's not related to the factors. And we can do something about specific variance. All right, so something we can do is allowing a correlation between indicators. So normally we're assuming that the indicators are independent. The only relationship between the indicators is what is coming from the factor. But let's say we did a survey and two of your items are reported by the child and one of your items is reported by the parent. These two items that are reported by the child might have more to do with each other simply because the child is the one reporting them and their perception is going to be slightly different from the parent. So in that case, they do have something to do with each other. There is variance explained there that's not attributed to the factor. It's external to the factor. It's the fact that the child reported it. This particular example is called shared method variance. But in general, you can have all kinds of shared variance that you might want to account for in your model. So another thing you might see is that there is overlap in wording. So when we get to the meme here, item 4 and item 6 have a very strong overlap in wording, a strong sense of belonging, a strong attachment. So that connection in wording could be what's causing this modification index here to say that our model might fit better if we allow these to correlate, right? There is some variance explained by these two that connects these two that's associated with the fact that they're both committed items, but there's an additional set of variance that's explained by the fact that they are so similar in wording. And yes, in general, you want to avoid this kind of thing, but it's allowable. And in this case, we have a good reason to allow it. Okay, so here's how we would add that correlation in the syntax. So in Stata, what we're going to do is we're going to have a statement that says cove. That means add a covariance, and the covariance is going to be between the error term of mean 4 and the error term mean 5, and mean 6. And you just have this little asterisk there to show that this is what is happening. In R, we don't have to specify that it's the error terms that are covariating. It's going to know that just because these are endogenous variables. So you can just put mean 4, and then the 2 tildes is how you indicate a correlation, mean 6. So if we add that covariance in there, what you can see is that we now get a line for it in our output. And we see that the correlation between the error term of mean 4 and mean 6 is 0.29, which is, moderate. So that it is actually, something there. And that would give us a slightly higher fit indices, slightly lower chi-square and higher fit indices. So this would make our model better to include this covariance here. But if you actually go back to our fit indices, this was pretty good even without that. So that modification was just to show you the idea of shared variance and to show you how the model could have been slightly better, but our model was really good also without that. Okay, so you'll see correlating errors pretty commonly in confirmatory factor analysis. All right, so back to our research questions about the mean. Is ethnic identity is measured by the mean one dimension or two dimensions. We saw that our model with one factor fit worse than our model with two factors. So it does seem that the mean is better represented with two factors, exploration and commitment. And then the second question is, do these items measure the subdimensions of the mean in the way that we think they do? And so we have multiple reasons to say yes. First, the model fit well. Second, all of our loadings were pretty high, above 0.6. I think 0.65 was the lowest one, and a lot of them were in the 0.7, 0.8 range. And then we had some reasonable correlations here. This correlation between expiration and commitment was pretty high, but we thought it was good. And if we had kept this correlation between mean 4 and mean 6, that was okay too, because it did make the model fit better. All right, so before we end, I'm just going to say a few words about the difference between exploratory and confirmatory factor analysis. So you might have heard of confirmatory factor analysis in other classes. Exploratory factor analysis in other classes. Exploratory factor analysis is not a structural equation modeling technique. Confirmatory factor analysis is a structural equation modeling technique, but they are connected. The main difference is in exploratory factor analysis, what you'll see is that you have no restrictions on the loading. Every factor loads on every indicator. In confirmatory factor analysis, we specify our model to say that no, factor 1 is only for indicator 1 and 2, and factor 2 is only for indicator 3 and 4. So that's the main difference. We're testing whether the model fits well when we say 1 and 2 with factor 1, 3 and 4 with factor 2. So this is the way you would make this match test is just by taking off the loadings or constraining the loadings factor 1 and 2 on factor 3 to 0. So if you think in matrices, this example might help. So these tables, imagine these are the covariance matrices between our 4 indicators. So in an exploratory factor analysis, we would have a correlation between every single indicator because we think they're all related to each other. But in confirmatory factor analysis, we would only have a correlation between indicator 1 and indicator 2, and indicator 3 and indicator 4. And these would be 0 because we think that the only relationship between, say, indicator 1 and indicator 3 is the correlation between those two factors. So this correlation right here would be everything that we allow to explain the variation between 1 and 3. There's nothing directly connecting them. All right, and then we're going to test if this is actually true by our model fit indices. So the analysis steps are going to be slightly different if you're doing EFA compared to CFA. If you're doing EFA, you're going to get the model. You're going to look at scree plots and eigenvalues. You're going to be doing rotations. You're going to be looking at the loadings, eliminating items, and repeating. If you're doing CFA, this should look familiar because it's the same step that we've been doing. There's still some, theory going in there, still estimating the model. You have this model fit step that's not in EFA. You can look at modification indices, but you respecifying model, respecifying, estimating, going back and forth. That's kind of similar. All right, so summary of confirmatory factor analysis. Our latent factors can have observed or latent indicators. You can do a CFA where your indicators are latent variables, but most often you're going to see latent variables with observed indicators. We're going to be looking at the loadings between the factor and the indicators. The difference between CFA and EFA is that we're restricting those factor loadings so that each item is only loading on one factor generally. But a special thing that we can do that we can't do in EFA is that we can allow error terms between items to co-vary. And that would suggest that there is some source of variance that's not attributable to the factor. And it could be due to wording, it could be due to method, lots of things. But we're acknowledging that by allowing those errors to correlate. Yeah, and we're going to be specifying our restrictions up front in CFA, the number of factors, which indicators are loading on which factors, what indicators are correlating, what factors are correlating. And the main thing here is that confirmatory factor analysis is going to be theory driven. Even though it's called confirmatory, it's not strictly confirmatory. As you saw, we can make modifications based on the modification indices. We can change things around based on what the data is showing us. We have an idea going in, but that idea has to be responsive to the data in a certain sense. So you're going to be paying attention to the fit of the model. You're going to be paying attention to what the loadings are, how the modification indices are suggesting you make changes to the model, and we're going to have this sort of, iterative relationship between theory and data with confirmatory factor analysis. So that's it.